Now let's look at how to testing an equation for symmetry property. There are three different types of symmetry property. One is symmetric with respect to x-axis, one is symmetric with respect to the y-axis, and the other one is symmetric with respect to the origin. So let's look at the definition first. A graph is said to be symmetric with respect to the x-axis if for every point xy on the graph and the point x negative y is also on the graph. Okay, so if you look at these 2 points, we can see they have same x coordinates, but y coordinates, one positive, one negative. Okay, that's the time we say the graph is symmetric with respect to the x-axis. Okay, so let's look at a graph so you can have a more visualized impression or idea. So this is kind of the graph we say symmetric with respect to the x-axis. So the half of the graph, which is in the red color, the other half in the blue color, okay, just let you see. Okay, every point on this half, if we denote as a point xy, and then you can find symmetrical point, okay, which is have the same x coordinates, but y coordinates have the opposite sign. Okay, if this is a positive, this one will be negative. And then all of them, okay, you can see from the graph. So symmetric with respect to the x-axis from the graph point of view actually is this half of the graph. If do the mirror image about x-axis, you will exactly get the other half. Okay, that's what it means, the graph symmetric with respect to the x-axis. So if we use a point as an illustration, okay, if a graph, we say symmetric with respect to the x-axis, and then the point 3, 2 is on the graph, and then the point 3, negative 2 must be also on the graph. Okay, same x, and then the y coordinates have opposite sign. Okay, if you graph it, 3, 2, that's the point 3, 2. Right? And then symmetric with respect to the x-axis, do the mirror image about x. So the symmetrical point should be this one, right? Same x coordinates, y coordinates do the opposite sign. So 3, negative 2 must be also on the graph. So you can think about do the mirror image about x-axis, and then that's how you got the other half, the other point. Now let's look at the definition to define symmetric with respect to the y-axis. A graph is said to be symmetric with respect to the y-axis if for every point xy on the graph and the point negative xy is also on the graph. So this time the y coordinates is the same, okay, while x coordinates one positive, one negative. All right, so let's look at the graph. That's what the graph look like, okay, when it's symmetric with respect to the y. So basically this blue colored, okay, that's half of the graph. If you do this blue color half, do the mirror image about the y-axis, and then you get exactly the red color, okay, right hand side of the other part. So that is the time we say graph symmetric with respect to the y. So if you notice every point, okay, on half, and then the symmetrical points must have the same y coordinates, but the x coordinates has the opposite sign. So let's try an exercise. Okay, if graph symmetric with respect to the y-axis, Okay, that means the y coordinates should be the same. Okay, if 5, 8 is on the graph, and then what point must be also on the graph? Y coordinates remain the same. Y coordinates need to be in opposite sign, right? If it's a 5, and then symmetrical point with respect to the y-axis should be negative 5, 8. The last symmetry definition, a graph is said to be symmetric with respect to the origin if every point xy on the graph, the point negative x, negative y is also on the graph. So symmetric with respect to the origin, both xy coordinates become opposite sign. Okay, both x. So that's negative x, negative y must also on the graph. So let's look at what the graph should be. So this half of the graph, okay, blue color, do the mirror image about the origin, about this point. Okay, so every point, if you connect symmetrical point, they should passing through the origin, okay, and have the same distance, right, away from origin. That's how to get each symmetrical point. So now let's try a single point, okay, as example. If graph symmetric with respect to the origin and the point 4, 2 is on the graph, then what's the other points must be also on the graph? Both x, y take the negative sign, right? Negative 4, negative 2 must be also on the graph based on the theorem. All right. So that's from graph point of view. Okay, we can visualize the symmetry property, so that's kind of easy. The more difficult part is how to testing for symmetry if not giving you the graph, instead giving you an equation. Okay, how to test symmetry. The procedure is summarized in this slide. In order to testing equation whether it's symmetric with respect to the x-axis or not, all you need to do is replace y coordinates by its negative y. Okay, so replace y by negative y, and then plug in to the equation and then simplify. If equivalent equation results, and then graph of the equation symmetric with respect to the x, otherwise no symmetric with respect to the x-axis. Okay, and very similarly, testing whether equation or the graph of equation symmetric with y-axis or not, you just simply replace x coordinates by its negative and then plug into the equation, simplify. If the resulting equation equivalent, and then we say equation symmetric with respect to the y-axis. For testing origin, both x and y replaced by its negatives, and then we plug in back to the equation, simplify. If resulting equivalent equation, and then we say graph of the equation symmetric with respect to the origin. It sounds pretty confusing, okay? They're all based on the symmetry property. So let's look at an example. Hopefully that will help you understand it better. Testing equation for symmetry. Okay, the given equation is y equals 4x squared divided by x squared plus 1. Okay, that's the given equation. Now we need to testing for all the 3 symmetry property. Okay, we're going to do it one by one. So first we're testing whether the graph of this equation is symmetric with respect to the x-axis or not. So what we need to do, we replace y by negative y and then plug in to the given equation. Okay, so we replace y by negative y. So left-hand side of equation is a negative y. Right-hand side, since doesn't have y, okay, no y involved on right-hand side of the equation, so we just write it. All right, and then let's look at this equation. This one we can further simplify, okay? We just leave like that. So after we replace y by negative y and simplify, this is the equation we have. Now we compare this equation to original given equation and see whether they are identical or equivalent. Obviously, the left-hand side, the sign is different, right? So it's not equivalent. Okay? So not equivalent. Therefore, not symmetric. The graph of this equation is not symmetrical with respect to the x-axis. I just write, I don't write a whole sentence, okay? Just use the cross represent no symmetrical property with respect to the x-axis. And then let's do the similar thing for the other axis, okay? Y-axis next. So what we need to do this time, we need to replace x by negative x and then plug in back to the equation, okay? So left-hand side, no x, we just copy y, and then 4 times negative x squared, right? Numerator replace x by negative x, denominator x squared, replace x by negative x squared plus 1, and then we simplify. We know positive x squared, negative x squared, after squaring it, right? The negative sign goes away. So it doesn't matter, this is replace x by negative x. After squaring it, it will be the same. So if we simplify, negative sign goes away. So that's numerator 4x squared, denominator is x squared plus 1. So after we replace x by negative x, that's the new equation. We have compared this with original equation. Are they equivalent? They are equivalent, right? Same, exactly the same. So that means the graph of this equation, it is symmetric with respect to the y-axis. Okay, now the next one, we test the origin. I don't have a, okay, let me try here, okay? Very small space. So testing whether it's symmetric with respect to the origin or not, I just write a short, okay? Instead of write a word origin, I just put the coordinates 0, 0 represent origin. So testing whether it's symmetric with respect to the origin or not, we need to replace both x and y by its negative, right? Okay, and then plug into the equation. So I don't have enough space. Again, I move to the top, okay? So replace y by negative y, replace x by negative x. And then simplify. Left-hand side, nothing we can simplify. We just leave negative y. Right-hand side, again, negative sign after squaring it is cancelled, right? Disappear. So right-hand side, we have this. This is after simplify, the new equation we have, right? Replace both x and y by its negative. After simplify, that's the new equation we have. And then compare this to original equation. Are they the same? Equivalent? No, right? Left-hand side missing the sign. So we conclude the graph for this testing equation is not does not symmetric with respect to the origin 0, 0. So if we summarize all the 3 symmetry properties, okay, the graph of this given equation is only symmetric with respect to the y-axis, okay, and then no any other symmetry property, only symmetric with respect to the y-axis. So if you review this example, what we're really looking for. Okay, is there any kind of pattern we can find here? Yes, we do. Okay, so basically, if the variable have even exponents, right, and then when we replace this variable by its negative, and then after simplify, the negative sign goes away, so it should be the same, right? But if the variable's exponents is an odd number, and then after we replace that variable by its negative, and then the negative sign will be remain, right? It will not be able to cancel out. So basically, the symmetry property we can easily determine by the exponents is an even number or odd number for each variable. So for this particular equation, we can see for variable x, okay, both variable x have the even exponents. So we know when replace x by negative x, and then the negative sign should cancel out, right? Should disappear. Therefore, from the exponents itself, we know it must symmetric with respect to the y-axis. Okay? It's not symmetric with respect to the x because variable y have the odd exponents. So when we replace y by its negative, it won't disappear, the negative sign. Okay? And then for the origin, we are testing whether x, variable x, variable y, both have even exponents or not, and then the x have even exponents, but the y have odd exponents. That's why it doesn't have symmetry property with respect to the origin. Okay, so that's kind of explains it from another point of view. Okay, the nature basically what the symmetry property, the testing, what we're doing actually, okay, is basically testing, whether the exponents on each variable is even number or is odd number. Okay, that's corresponding to symmetric property. So hope that helps you understand the symmetry testing a little bit. So that's book given a very detailed explanation, okay, the same as I just showed you. This is, after same equation, okay, we have earlier, and then if we use graphic calculator to plot this equation, and then we can verify our solution, okay, the graph, it is symmetric with respect to the y-axis only. No symmetry property with respect to the x-axis, and then no symmetry property with respect to the origin. Okay, so you can always use your graphic calculator to testing, okay, whether the symmetry property you conclude is correct or not.